Now let us continue our discussion of the linear array. In the previous part, we obtained the array factor in this form, and here we take its absolute value, because the amplitude is what matters. As one important example, let us consider the case alpha equals 0. That means that all elements are excited in phase, with no progressive phase shift. This configuration is called a broadside array. I will explain the reason for that name. In this case, the maximum, which is called the main lobe, occurs at u equals 0. Since alpha is 0, the factor u plus alpha also becomes 0 there, and therefore the array factor takes its maximum at u equals 0. Now u is equal to kd cosine theta. So if u is 0, cosine theta must be 0, and therefore theta is equal to pi over 2. Theta equals pi over 2 means the direction perpendicular to the array axis, that is, the direction in the xy plane. So the strongest radiation is emitted in the direction normal to the array. That is why this configuration is called a broadside array. Broadside means the direction perpendicular to the array axis. Next, let us think about the width of the main lobe. We already know that the maximum occurs at theta equals pi over 2, but we would now like to know how wide the main lobe is. In other words, we want to know where the array factor decreases from its maximum value and first becomes 0. The width of the main lobe is called beamwidth. The point next to u equals 0, where the array factor becomes 0, can be used to define the beamwidth. The 0 occurs when the numerator becomes 0. The nearest 0 is obtained when the argument of the sign becomes plus or minus pi. That is, u sub z is obtained as shown in this expression. Let us denote the angle at the first null by theta sub z. Using u equals kd cosine theta, and chi, the wave number, equals 2 pi over lambda, we obtain cosine theta sub z equals lambda divided by 2n plus 1 times d. Typically, the main lobe is narrow, so theta sub z is very close to the maximum angle pi over 2. So we may approximate cosine theta by its Taylor expansion around theta equals pi over 2, as given in this expression. Because the positive and negative sides are symmetric, we only need to consider the positive side. Let us therefore write theta sub z as pi over 2 minus delta theta. Then the deviation from pi over 2 is just delta theta. Substituting this approximation, we find that delta theta is approximately lambda divided by 2n plus 1 times d. The nulls appear on both sides of the maximum, so the beamwidth between the first nulls is approximately 2 delta theta. Here we denote 2n plus 1 times d as capital L. The beamwidth is approximately 2 lambda over L. L is the total array length, because the distance between each element is d, and we are considering 2 n plus 1 elements. This is an important conclusion. The beamwidth is determined by the total array length. If we increase the number of elements while keeping the spacing the same, the total length becomes larger and the beam becomes narrower. However, if we simply pack more elements into the same total length by reducing the spacing d, the beamwidth does not become narrower. In other words, what matters is not only the number of elements, but the overall length of the array. This is very important in applications such as radar. If we want high angular resolution, we need a narrow beam. And to obtain a narrow beam, we need a sufficiently long array, or a shorter wavelength. That is the main physical conclusion of this discussion.